It's one of the most recognizable locomotives in the world, a symbol of modern freight trains. Long, heavy, and constant. 6 axles, 4,400 horsepower, and that distinctive boxy profile with radiator wings that announce its presence from miles away. It powered the rise of intermodal shipping, mega coal trains, and double-stack container corridors across North America. It became the workhorse that railroads could depend on, day after day, year after year, in scorching desert heat and freezing mountain passes. And today, nearly 30 years after its debut, the GE-9 remains the backbone of modern railroading. This is the story of how a single locomotive design changed the freight industry forever. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. For decades, the electromotive division dominated the American locomotive market. EMD was the name that defined railroading. Their SD42, introduced in 1972, became the standard by which all other freight locomotives were measured. Reliable, powerful, and proven across every railroad in North America, the SD42 was everywhere. Alongside it, models like the GP38-2 filled out rosters from coast to coast. GE was the challenger, the underdog. Throughout the 1970s, General Electric had been building locomotives, but they were always playing catch-up to EMD's dominance. Their U-boat series locomotives, the U-23B, U-30C, and others, were solid machines, but they never quite captured the market share that EMD enjoyed. Railroads trusted EMD. GE was the alternative, the backup option, the locomotive you bought when EMD couldn't deliver fast enough. But GE was learning. Every locomotive they built, every failure, every success, taught them something new about what railroads really needed. By the early 1980s, they were ready to make their move. In 1984, GE introduced the -8 line. The B-23-7 and C-37 gave way to the -840B, the -840C, and the -840CW. These locomotives represented the first real threat to EMD's dominance. They were modern, they were powerful, and most importantly, they were reliable. Railroads began placing larger orders. Conrail bought them, Norfolk Southern bought them, CSX bought them. Suddenly, GE wasn't just the alternative anymore. They were a legitimate competitor. The freight market itself was shifting during this time. Trains were getting longer, loads were getting heavier. The rise of intermodal shipping meant that railroads needed locomotives that could pull double-stack container trains across the continent at consistent speeds. Coal traffic from the Powder River Basin in Wyoming was exploding, requiring massive consists of locomotives to haul 100-car coal drags over mountain grades. What railroads discovered was that they didn't just need raw horsepower. They needed reliability. They needed locomotives that could run for weeks without major maintenance. They needed fuel efficiency. They needed machines that could be repaired quickly when something did go wrong. The -8 proved that GE understood these needs better than anyone else. But by the early 1990s, GE knew they couldn't rest on the success of the -8. EMD was developing their own next-generation locomotives. The competition was fierce, and the railroad industry was consolidating rapidly. Mergers were creating mega railroads that would place massive orders for hundreds of locomotives at a time. Whoever built the best locomotive for this new era would dominate the industry for decades. GE realized a new generation was needed. They needed to build something better than the -8, something that would cement their position as the leader in freight locomotive manufacturing. And so, in the early 1990s, work began on what would become the -9. In the early 1990s, GE engineers gathered around one goal: build the most reliable, most economical, and most powerful freight locomotive ever made. Not the fastest, not the flashiest, but the one that railroads would want to buy by the hundreds and keep running for decades. Development of the -9 began around 1993. The design philosophy was clear from the start. This wouldn't be a radical departure from the -8 platform. Instead, it would be an evolution. Take everything that worked, refine it, simplify it, and make it even more maintainable. GE had learned that railroads didn't want cutting-edge technology that might fail in unexpected ways. They wanted proven technology, refined to near perfection. The foundation of the -9 was the GE 7FDL16 engine. This 16-cylinder, four-stroke diesel engine had been the heart of GE locomotives for years. But for the Dash 9, it was refined even further. Engineers focused on reliability and maintenance intervals. Every component was designed to last longer, to be easier to replace, and to require less frequent attention. The goal was 10,000 hours between major maintenance events. That's over a year of continuous operation. The engine was rated at 4,400 horsepower. This wasn't about chasing horsepower numbers. It was about delivering consistent, reliable power across the entire operating range. The 7FDL16 in the Dash 9 configuration produced a smooth power curve that gave engineers exactly what they needed, whether starting a heavy train from a standstill or maintaining speed on a long grade. But the real innovation in the Dash 9 wasn't just the engine, it was the electronics. GE equipped the Dash 9 with advanced microprocessor controls that were a generation ahead of anything in the Dash 8. These systems managed everything from wheel slip correction to fuel injection timing. The computer could detect the beginning of a wheel slip event and adjust power delivery in milliseconds before the wheels even lost significant traction. This meant better adhesion, less wheel wear, and more efficient power transfer to the rails. The electronics were also modular. If a circuit board failed, a mechanic could pull it out and replace it with a new one in minutes, rather than spending hours troubleshooting individual components. This design philosophy extended throughout the locomotive. Everything was designed to be maintained quickly and efficiently. GE also introduced the wide-nose safety cab as an option. The Dash 944 CW, the CW standing for Comfort Cab Wide Nose, featured a nose section that extended the full width of the locomotive. This design provided significantly better crashworthiness in the event of a collision. It also improved ergonomics for the crew, with better visibility, improved HVAC systems, and a more spacious working environment. Railroads could order their Dash 9s with either the wide nose or the traditional narrow nose, depending on their preferences. The traction system remained DC, or direct current. While AC traction was beginning to emerge as the next big thing in locomotive technology, GE made a deliberate choice to stick with DC for the Dash 9. DC traction motors were proven, reliable, and well understood by railroad maintenance crews. They provided massive low-speed tractive effort, which was exactly what railroads needed for starting heavy trains and climbing grades. The GE 752 traction motors in the Dash 9 could deliver incredible pulling power when it mattered most. The Dash 9 was designed from the ground up for the modern freight railroad. It was built for intermodal trains, for coal drags, for manifest freight, for distributed power consists, where multiple locomotives spread throughout a train would work together under computer control. Every detail, from the radiator design to the fuel tank capacity to the layout of the electrical cabinet, was optimized for one thing: keeping freight moving, reliably and economically. By 1994, the first Dash 9s were rolling off the assembly line at GE's Erie, Pennsylvania facility. Railroads were waiting. Let's talk about what makes the Dash 9 tick. This is where engineering becomes art, where thousands of design decisions come together to create a machine that can haul 10,000 tons across a continent. The prime mover is the heart of any locomotive, and in the Dash 9, that heart is the GE 7FDL16. 16 cylinders arranged in a V configuration. Each cylinder displaces 9 by 10.5 inches. That's bore by stroke. When all 16 cylinders are firing at full power, this engine produces 4,400 horsepower at 900 RPM. But raw horsepower is only part of the story. What makes the 7FDL16 special is how it delivers that power. The engine uses a turbocharged design, with exhaust gases spun through a turbocharger to force more air into the cylinders. More air means more complete combustion, which means more power and better fuel efficiency. The turbocharger on the 7FDL16 is massive, a precisely engineered piece of machinery that has to withstand extreme temperatures and pressures while spinning at tens of thousands of RPM. The fuel injection system is equally sophisticated. Each cylinder has its own fuel injector, computer-controlled to deliver exactly the right amount of diesel at exactly the right moment in the combustion cycle. The timing of fuel injection has a huge impact on efficiency and emissions. Too early, and you waste fuel. Too late, and you lose power. The computer manages this thousands of times per second, constantly adjusting to maintain optimal performance. One of the key design goals for the 7FDL16 and the Dash 9 was extended maintenance intervals. GE engineers obsessed over every detail that could affect reliability. Oil filters were oversized to extend service life. Cooling systems were designed with extra capacity to prevent overheating. Bearing surfaces were hardened to reduce wear. The result was an engine that could run for 10,000 hours between major overhauls. That's not just a marketing number. That's real-world performance that meant railroads could keep locomotives in service longer, reducing downtime and maintenance costs. The engine also needed to be fuel efficient. A freight locomotive might burn hundreds of gallons of diesel per hour when working hard. Over a year, over a fleet of hundreds of locomotives, small improvements in fuel efficiency translate to millions of dollars in savings. The 7FDL16 achieved this through precise control of the combustion process, maintaining optimal air-fuel ratios across the entire power range. Now, all that power from the engine doesn't go directly to the wheels. It goes to a generator. The 7FDL16 drives a massive electrical generator that produces electricity. That electricity then powers traction motors on the axles. This diesel-electric design has been the standard for decades because it's incredibly efficient. The engine can run at its optimal speed, while the traction motors can turn at whatever speed the train needs. This is where the microprocessor controls become critical. The computer system in the Dash 9 manages the entire power flow from engine to wheels. When the engineer moves the throttle, the computer decides how much power to request from the engine and how to distribute that power to the 6 traction motors. This isn't a simple linear relationship. The computer has to account for rail conditions, wheel slip, grade, speed, and a dozen other factors. Wheel slip is one of the biggest challenges in locomotive operation. When a wheel begins to slip on the rail, it's losing traction, which means it's not contributing to pulling the train. In older locomotives, wheel slip could be a serious problem, especially in wet or icy conditions. The Dash 9's computer system revolutionized wheel slip control. It monitors the rotational speed of every wheel constantly. If one wheel starts to turn faster than the others, even slightly, the computer knows it's beginning to slip. In milliseconds, the system can reduce power to that specific traction motor, allowing the wheel to regain adhesion and then smoothly increase power again. This all happens faster than any human operator could react. The result is better adhesion, which means more of the locomotive's power actually goes into pulling the train rather than spinning wheels. It also means less wear on wheels and rails. Slipping wheels create heat and friction that can damage both the wheel and the rail surface. By preventing excessive wheel slip, the Dash 9's control system extends the life of these expensive components. The traction motors themselves are GE 752 model DC motors. Each motor is mounted in a truck, the frame assembly that holds the wheels and axles. The Dash 9 has 2 trucks, each with 3 axles, for a total of 6 axles and 6 traction motors. These motors are enormous, powerful pieces of equipment. Each one produces tremendous torque, especially at low speeds. DC traction motors have a natural characteristic that makes them perfect for railroad service. They produce maximum torque at 0 speed. That means when a train is stopped and needs to start moving, the motors can deliver their full pulling force immediately. As the train speeds up, the torque gradually decreases, but the horsepower remains roughly constant. This torque curve is ideal for freight service, where starting heavy trains and climbing grades are the most demanding operations. The GE 752 motors are also remarkably durable. They're designed to handle the thermal stress of continuous operation, the mechanical stress of varying loads, and the electrical stress of rapid power changes. Inside each motor is a complex assembly of copper windings, steel laminations, and carbon brushes. The brushes transfer electrical current to the rotating armature inside the motor. These are wear items that need periodic replacement, but they're designed to last for months of heavy service. Cooling is critical in a locomotive. The engine generates tremendous heat. The electrical generator generates heat. The traction motors generate heat. All of this heat has to be dissipated, or the locomotive will overheat and shut down. The Dash 9's cooling system is a masterpiece of thermal management. Those distinctive radiator wings on top of the locomotive are hard to miss. They're not just for looks. Inside those housings are massive radiator cores, similar in concept to the radiator in a car but scaled up enormously. Coolant circulates through the engine, absorbing heat, and then flows through these radiators where fans blow air across the fins to cool it back down. The Dash 9's radiators are oversized compared to earlier locomotives. This gives extra cooling capacity, which is essential when working in desert heat or climbing long mountain grades where the engine is working at full power for hours. The fans themselves are powerful, capable of moving huge volumes of air through the radiator cores. They're electrically driven and computer controlled. The system monitors coolant temperature constantly and adjusts fan speed as needed. In cold weather, the fans might barely run. In hot weather or under heavy load, they'll spin at maximum speed, forcing air through the radiators to keep temperatures under control. The cab design of the Dash 9 represented a significant step forward in crew, comfort, and safety. The wide-nose design, in particular, was a response to years of accidents that showed traditional narrow-nose locomotives provided inadequate protection in collisions. The wide nose extends the full width of the locomotive frame, creating a crumple zone that absorbs impact energy. In the event of a collision, this design provides significantly better protection for the crew. Inside the cab, the control stand features a more ergonomic layout than earlier locomotives. The throttle, dynamic brake, and air brake controls are positioned for easy reach. Gauges and displays provide the engineer with all the information needed to operate the locomotive efficiently. The HVAC system is more powerful and more reliable, which might not sound important until you consider that engineers spend entire shifts in that cab, sometimes in extreme heat or cold. Visibility is also improved in the wide-nose design. The windshield wraps around, providing better sightlines down the sides of the locomotive. This is critical when operating in rail yards or in situations where the engineer needs to watch for signals or hazards alongside the track. All of these systems, the engine, the generator, the traction motors, the electronics, the cooling system, the cab, work together as an integrated whole. The Dash 9 isn't just a collection of components. It's a carefully engineered system where every part is designed to work with every other part. That's what makes it so reliable. That's what makes it so effective. And that's why railroads loved it. By the late 1990s, one thing was clear. The Dash 9 wasn't just successful. It dominated the continent. It became the standard locomotive for modern freight operations, the machine that railroads turned to when they needed reliable power for their toughest assignments. The orders came flooding in. Burlington Northern Santa Fe Railway placed massive orders, eventually building the largest fleet of Dash 9s of any railroad. Their distinctive orange and black units became synonymous with Western railroading. Norfolk Southern ordered hundreds of units in their classic black paint scheme. Canadian National, operating across Canada's vast distances and harsh climate, found the Dash 9 perfectly suited to their needs. Union Pacific, CSX, every major railroad wanted them. By the time production wound down, over 3,500 Dash 9 units had been built. That's an extraordinary number for a single locomotive model, but numbers alone don't tell the story of why the Dash 9 became so dominant. To understand that, you have to look at how railroads actually use these machines. The Dash 9 became the standard power for double-stack container trains running from West Coast ports to Midwest distribution centers. These trains are the backbone of modern commerce. Consumer goods from Asia arrive at Los Angeles or Long Beach, get loaded onto double-stack well cars, and head east. A typical intermodal train might stretch a mile or more, with containers stacked too high on specialized cars. These trains need to run fast and run on schedule. The Dash 9 could maintain track speed hour after hour, day after day, with minimal maintenance. In the Powder River Basin of Wyoming, Dash 9s became the workhorses of coal traffic. The PRB is one of the largest coal-producing regions in North America. Unit trains, trains carrying nothing but coal from a single mine to a single power plant, run constantly. These trains are heavy. 100 hoppers loaded with coal can weigh 15,000 tons or more. Getting these trains moving, and especially getting them over the steep grades leading out of the basin, requires enormous tractive effort. Dash 9s excelled at this work. Their DC traction motors could deliver the low-speed pulling power needed to start these massive trains, and their reliable engines could pull them over the mountains. Long-haul manifest freight, trains carrying a mix of different car types with different cargoes, also relied heavily on Dash 9s. These trains might carry anything from lumber to steel coils to auto parts. They stop at multiple yards along their route to drop off and pick up cars. The locomotives need to be flexible, able to handle varying train lengths and weights. The Dash 9's consistent performance made it ideal for this service. What railroads loved most about the Dash 9 was its maintainability. In the railroad industry, a locomotive sitting in the shop is a locomotive that's not making money. Every day a unit is down for maintenance is a day it's not pulling trains. The Dash 9's modular design meant that when something did break, it could usually be fixed quickly. The extended maintenance intervals meant locomotives could stay in service longer between shop visits. The reliable 7FDL16 engine meant fewer catastrophic failures that would require major overhauls. Fuel efficiency was another key factor. Diesel fuel is one of the largest operating expenses for any railroad. Even a small improvement in fuel consumption, multiplied across a fleet of hundreds of locomotives running hundreds of thousands of miles per year, adds up to enormous savings. The Dash 9's computer-controlled fuel injection and optimized engine management delivered this efficiency. Railroads tracked fuel consumption carefully, and the Dash 9 consistently performed well. The locomotives also proved remarkably adaptable to different climates. Dash 9s worked just as reliably in the desert, heat of Arizona and New Mexico as they did in the frozen winters of Montana and Canada. The oversized cooling system handled extreme heat. The robust construction handled extreme cold. This versatility meant railroads could deploy Dash 9s anywhere in their system without worrying about climate-specific limitations. There was also something intangible about the Dash 9 that contributed to its success. It became an icon. Rail fans loved them. The distinctive profile, the sound of the 7FDL16 engine at full power, the sight of a long, consist of Dash 9s leaning into a curve with a mile-long freight behind them. These became defining images of modern railroading. Railroad employees respected them. Engineers knew they could depend on a Dash 9. Maintenance crews knew how to work on them. Dispatchers knew they would perform reliably. The Dash 9 era represented a shift in the locomotive industry. GE had not only caught up to EMD, they had surpassed them. The orders kept coming. Railroads that had been loyal EMD customers for decades started buying GE. The success of the Dash 9 positioned GE as the dominant locomotive manufacturer in North America, a position they maintain to this day. By the early 2000s, you could travel almost anywhere in North America and see Dash 9s at work. They were pulling grain trains across the prairies of Kansas. They were hauling lumber through the mountains of British Columbia. They were moving chemicals through the Gulf Coast. They were everywhere, doing everything, reliably and efficiently. The Dash 9 became more than just a successful product. It became the standard by which other locomotives were measured. When railroads evaluated new locomotive models, they would inevitably compare them to the Dash 9. Could the new model match the Dash 9's reliability, its fuel efficiency, its maintainability? Often the answer was no. The Dash 9 set a bar that was difficult to exceed. This dominance also created a self-reinforcing cycle. Because so many Dash 9s were in service, maintenance crews became experts at servicing them. Parts were readily available. Best practices for operation and maintenance were well established. This made Dash 9s even more attractive to railroads, which led to more orders, which reinforced their position as the standard. It was a virtuous cycle that kept the Dash 9 at the center of North American freight railroading for years. The success of the basic Dash 9 to 44 CW platform led to numerous variants and adaptations, each designed to meet specific railroad needs or operating conditions. These variations show how a fundamental design could be modified and improved to extend its usefulness. The Dash 944 CW was the standard model, the one most people think of when they hear Dash 9. Wide cab, DC traction, 4,400 horsepower, 6-axle design. This was the baseline from which everything else derived, but not all railroads wanted exactly the same configuration. Canadian National preferred a different cab design. They ordered units with what's known as a Canadian Comfort Cab, or North American Safety Cab. This design, designated C44-9W on CN units, featured a distinctive curved windshield profile that some referred to as a gooseneck. The cab provided excellent visibility and was specifically designed to meet Canadian safety regulations and climate requirements. CN's vast network stretches across some of the harshest territory in North America. From the Rocky Mountains to the frozen prairies to the maritime provinces, their Dash 9s needed to handle everything, and the comfort cab design provided additional protection and comfort for crews working in extreme conditions. Some railroads also ordered Dash 9s with narrow noses rather than the wide-nose design. These units, often designated C44-9 without the W suffix, featured the traditional narrow nose similar to earlier locomotives. While the wide nose provided better crash protection, some railroads preferred the narrow nose for various operational or aesthetic reasons. The mechanical components remained the same regardless of nose configuration. As the Dash 9 fleet aged, railroads faced a choice. They could retire these locomotives and buy new ones, or they could rebuild them to extend their service life. Given the cost of new locomotives and the proven reliability of the Dash 9 platform, rebuilding made tremendous economic sense. This led to some of the most interesting variants of the Dash 9 design. Norfolk Southern developed the most ambitious Dash 9 rebuild program. Their AC44C6M program took older Dash 9s and completely remanufactured them with AC traction. AC, or alternating current, traction represents a significant technological advancement over DC systems. AC motors provide better wheel slip control, higher tractive effort, and improved performance in heavy haul service. NS partnered with Progress Rail, which had acquired EMD, to perform these conversions. The locomotives received new Caterpillar engines, new AC traction inverters, and new three-phase AC traction motors. The result was essentially a new locomotive built around the existing Dash 9 frame and trucks. These rebuilt units received new life with decades of additional service potential. Union Pacific and BNSF also developed their own Dash 9 rebuild programs. UP's program focused on updating the electronics, installing modern microprocessor systems, and overhauling the mechanical components while retaining the DC traction system. BNSF took a similar approach, extending the life of their massive Dash 9 fleet through systematic rebuilding and upgrading. These programs make economic sense when you consider that a rebuild costs a fraction of a new locomotive's price. Some Dash 9s also received emissions upgrades to comply with increasingly strict environmental regulations. The Environmental Protection Agency has implemented tiered emissions standards for locomotives, with each successive tier requiring lower emissions of particulates and nitrogen oxides. Many Dash 9s were upgraded to Tier 0 Plus or Tier 1 Plus standards through the installation of cleaner burning fuel injectors, improved combustion management, and other modifications. While not as clean as brand new Tier 4 locomotives, these upgrades allow older Dash 9s to remain in service while reducing their environmental impact. The Dash 9 platform also found success internationally. GE built export versions adapted to the requirements of foreign railways. In Brazil, Vale, the mining company, operates GE C40 9W locomotives, which are essentially Dash 9s adapted to metric gauge and Brazilian operating conditions. These locomotives haul massive iron ore trains from inland mines to coastal ports. The tropical climate and mountainous terrain of Brazil present different challenges than North American operations, but the fundamental reliability of the Dash 9 design proved adaptable. Australian Railways also received Dash 9 derivatives. The GT46C locomotives built for Australia by a GE licensee share many design elements with the Dash 9, including the 7FDL16 engine and similar electrical systems. These locomotives work in some of the most remote and harsh conditions on Earth, hauling freight across the Australian outback. Even Indian Railways has incorporated GE design elements influenced by the Dash 9 era into their fleet. While not direct copies, many Indian diesel locomotives use technology and design principles proven in locomotives like the Dash 9. The success of these international adaptations demonstrates that the Dash 9's core engineering principles, reliability, maintainability, and robust design, translate across different operating environments and railway cultures. Modern Dash 9 fleets continue to evolve. Many units now feature updated paint schemes as railroads have merged or rebranded. Former Burlington Northern units now wear BNSF orange. Former Conrail Dash 9s operate in Norfolk Southern black or CSX dark blue. Some units have been sold to regional railroads or leasing companies, where they continue to work on smaller operations. Advanced monitoring systems have been retrofitted to many Dash 9s. These systems collect data on engine performance, fuel consumption, and component condition, transmitting it wirelessly to railroad maintenance centers. This allows predictive maintenance, identifying potential problems before they cause failures. A bearing that's running hot, a fuel injector that's performing below specification, a cooling system that's not maintaining proper temperature ACE. All of these can be detected and addressed before they strand a train. Some railroads have also experimented with remote control systems on Dash 9s used in yard service. These systems allow a single operator on the ground to control a locomotive via a belt pack radio control unit, eliminating the need for a crew in the cab during switching operations. This technology improves safety and efficiency in rail yards. The sheer number of Dash 9s still in active service today, nearly 30 years after the first units were delivered, speaks to the quality of the original design. Many of these locomotives have accumulated millions of miles. They've crossed the continent thousands of times. They've hauled billions of tons of freight, and they're still working. With proper maintenance and periodic rebuilding, there's no reason many of these units can't continue working for another 20 or 30 years. This longevity is remarkable in an industry where technological change is constant. Newer locomotives with AC traction, Tier 4, emissions compliance, and advanced computer systems have come along. But the Dash 9 remains relevant because it does its job so well. It's not the flashiest technology anymore, but it's proven technology. And in the railroad business, proven reliability is worth more than cutting-edge features. The Dash 9 wasn't the fastest locomotive ever built. It wasn't the newest. And it wasn't the most advanced, but it was exactly what railroads needed at the moment they needed it. Reliable, efficient, nearly unstoppable. It arrived at a pivotal time in railroad history when the industry was consolidating, when trains were getting longer and heavier, when intermodal shipping was transforming how goods moved across continents. The railroads needed a locomotive they could depend on absolutely, a machine that would start every time, run day after day, and require minimal maintenance. The Dash 9 delivered. GE's success with the Dash 9 fundamentally changed the locomotive industry. It established GE as the dominant manufacturer, a position they hold to this day. It proved that reliability and maintainability could be more valuable than raw technological advancement. It showed that evolutionary improvement of a proven design could be more successful than revolutionary new approaches. But beyond the business success, beyond the market share and the production numbers, the Dash 9 became something more. It became an icon of modern railroading. That distinctive profile, those radiator wings, that deep rumble of the 7FDL-16 at full power, these became the signature of freight rail in the late 20th and early 21st centuries. Today, when you watch a freight train roll past, there's a good chance you're watching Dash 9s at work. They're still pulling intermodal trains from the West Coast. They're still hauling coal from the Powder River Basin. They're still moving manifest freight across the prairies and through the mountains. Many have been rebuilt, upgraded, and modernized. But they're still working, still reliable, still doing exactly what they were designed to do 3 decades ago. The legacy of the Dash 9 is visible every day on railroad lines across North America and beyond. Every freight train that delivers goods on time, every ton of coal that reaches a power plant, every container that moves from ship to rail to truck, the Dash 9 played a part in making that system work. It became the foundation of modern freight logistics, the reliable workhorse that kept the supply chain moving. In an industry measured in decades where decisions made today affect operations for a generation, the Dash 9 stands as a testament to what can be achieved through careful engineering, attention to detail, and a deep understanding of what customers actually need. It wasn't designed to be revolutionary. It was designed to be right, and that made all the difference. Nearly 30 years after the first unit entered service, the GE-9 remains the backbone of modern freight railroading, not because it's the newest or the most advanced, but because it works. And sometimes that's all that matters.